Okay, so now let's look at topic 12, electric fields, question 1. A small positive charge is placed at L inside a uniform electric field and experiences a force of magnitude F. The charge is then moved from point L to point M. What is the change in potential energy? Okay, so let's look at the answers first. We have either gain or loss of potential energy, and this is the magnitude. Okay, now energy has the same units as work done. Okay, and work done is defined as force times distance. Correct? This distance is now the distance moved in the direction of the force. Okay, so now the electric field lines are, you can say that they indicate the direction of the force. That means, so as you can see, the electric field lines are all pointing from the left to the right, correct? Indicated by the arrowhead here. That means if let's say I put a charge here, okay, a positive charge. This means the force, there's only a force acting in this direction. Is there any vertical component of the force? No, there's none, right? Because the arrow do not point downwards or upwards. So therefore, there is only Fx and there is no Fy, or rather the vertical component is 0. Okay? So therefore, any vertical movement in this direction means if a charge move from here to another place directly below it or on top of it, there will be no work done. Okay? Because again, work done is force and times the distance moved in the direction of the force. So the force is pointing from left to right. If you move up and down, there's no work done. Okay? Now this charge moves from L to M. So there is some vertical component movement and there is some horizontal movement. But as we concluded earlier, any vertical movement will not be counted. Correct? It doesn't contribute to the work done. Only the horizontal movement. So therefore answers B and D must be wrong. Okay? B and D, this square root x squared plus y squared is simply your Pythagoras theorem, okay, which is essentially this distance from L to M. Okay, but we only want this distance, which is the x distance. Okay, x. So therefore the magnitude MAG, magnitude of this potential energy must be Fx. So now we have to determine if it's a gain or it's a loss. Okay, so how do we determine if it's a gain or a loss? As you can see, this electric field line is pointing from the left to the right, right? That means we can pretend that there is a positive plate here, plus for positive, and a negative plate here. Why do I want to do that? A negative plate, correct? Because electric field lines always point from the positive to a negative plate, correct? So therefore, the potential lines will be arranged as such. There will be such potential lines getting from more positive to more negative. So therefore, the electric field lines point from left to right. Now, potential energy, let me use PE. PE is, if you look at your equations table, it will be potential times charge, correct? In this case, this Q is positive. So the V here is positive and the V here is negative, correct? So therefore, the potential energy final F minus the potential energy initial must be equals to, finally is negative, right? So we write negative times Q minus positive times Q, correct? And negative minus a positive, minus positive, that means just minus, right? So negative minus positive will give me negative, right? Times Q. Therefore, it has to be a loss, correct? That means you lose potential energy. We can just to give you an example, if the positive and negative is a bit confusing, why don't we just sub in values? Okay, so let's say this is negative 10, right, and that's positive 10. So we negative 10 minus away positive 10. What will you have? Negative 10 minus positive 10, you have negative 20, correct? So you can see here it's negative, right? So this indicates there's a loss of potential energy.